Welcome everyone to the first Space Syntax Lab seminar in the new academic year. We're excited to welcome Dr. Dalton, who will talk about embracing organic patterns to make sustainable neighborhoods. This seminar will delve into the challenges and methodologies of defining neighborhood boundaries, exploring their impact on sustainable urban design and social dynamics within communities. And Dr. Dalton is a distinguished member of the Space Syntax community, recognized for his prolific contribution to the field. He's a reader in computer science at the Northumbria University and a member of the Space Syntax North Group. Dr. Dalton has been a trailblazer, playing a pivotal role in shaping the early landscape of analytical software, including groundbreaking tools such as Axman, Spacebox, Meander, and WebMap at home. Collaborating with Professor Ruth Dalton, Sheep's work has been influenced the trajectory of space syntax theory, particularly in relationship to incorporating angularity as a key factor in spatial analysis. He has further extended this understanding by delving into the mathematical foundations of integration in isovist fields and the benefits of stochastic isovists. Dr. Dalton's doctoral research was focused on comprehending and uncovering the intricacies of neighborhoods with spatial representations, employing local synergy and intelligibility measures. And with this, I'd like to hand over to Sheep. And if there are any questions, please put them in the chat. We will have a Q&A at the very end. And unless there's something like really urgent, which Sheep might address in his talk directly.
Ooh, can I see the chat? I've lost the chat box now. I've gone into slideshow mode. Okay. If anyone sees a chat go by, let me know.
I will have my eyes on the chat.
Okay, good. Okay, the first slide you've just kind of had, I've had a very excellent and flattering introduction. It's a great honor to kind of lead off this new series of space syntax lectures. That's really fantastic. This work stretches back to 2009, but it's actually based on a recent publication I've just done. Let's start off with, it's quite common to sort of see adverts like this where people talk about kind of, oh, we are building your neighborhood. And that actually touches on something that's actually been a kind of an issue in architecture and urban planning for a very long period. And that's the question of, is neighborhood susceptible to design? Today what I'm going to briefly cover is basically a kind of short history of neighborhoods, some work on neighborhood finding, core work on how to measure a neighborhood, which if you're a space syntax student or a researcher looking for a new idea could be quite useful. The latest research on how to create a representative view, which is kind of the work I'm kind of have most recently done. An example of deconstructing results, and this is like me just kind of going, oh, I really wish I'd spent more time doing this because this is kind of quite fun to do. So again, this was something I did during my PhD, but I think again, is there to kind of inspire. And then we'll have some questions if available. And there's lots of ways we can move off in many different directions. Right, okay, so back to neighborhood. So the desire to create neighborhood has been quite a long one. It goes back to say, the Perry neighborhood unit that was kind of rough in the late 1890s. So people have been trying to create neighborhoods for a very long period. The city garden movement, which gave rise to a lot of sort of cities in the UK, the places like Welwyn Garden City and stuff. These were all creations of trying to create a neighborhood. The City Beautiful movement sort of came out of the garden movement, but was a bit more urban. Kind of like had its heyday about the 20s. Again, I'm being a bit kind of rough and ready with the numbers. New urbanism came out in the 80s. And again, that was an American kind of attempt to, again, try and create an urban feel for being in response to what's kind of social geographers like Tuan said was placelessness. And again, we're going to be running on the borders of geography, social geography for a bit for this talk. And then more recently, we've had the urban village movement, which was something that happened in the UK. So yeah, I don't know quite recently what's happened. I don't know quite recently what's been happening in terms of that, but I think a lot of people are still trying to create neighborhood. Equally long has been the supposition that this cannot be done. So you had Mark Webber in the 1960s who came up with this great line, which is like, you can have community without propinquity, i.e. you don't have to be near someone to have a community with them. So therefore, do we really need neighborhoods? And then you've got great lines like people like Emily Talon wrote, planners need to detach themselves from the idea of physical planning can create a sense of community. This was in a critique of new urbanism. And again, so it creates the fact that there is this debate about whether or not neighborhoods actually exist. Are they actually real? Do they actually, and if they are real, can architects and urban planners actually do anything to make them? For example, in the kind of world of urban geography, they have this kind of proof that that place, neighborhood, for example, neighborhood is a kind of a place, is unrelated to space. And the Susan Langer's example from the 1950s was basically, you can have people on a ship, and people on a ship, the ship is moving, but the ship is a place. The Titanic is a place. The Queen Mary is a place. Equally, you can have a gypsy camp. And, at one point you could have a gypsy camp there, or an Indian, Native American camp, as we would say now. They can be they have a place, but the place moves around with them. More recently, Harrison and Dorish sort of said, you could have a place, you could have like a festival somewhere like Burning Man or Glastonbury, and it becomes a place for a bit. And then you could have a completely different festival, and that becomes another place, and their kind of response is, well, what gives with that? So for them, for Harrison, a location is always there, but place is how it's used. Weirdly enough, this notion goes all the way back to the ancient Greeks, where they had this concept of chora, a spatial location, and topos, place. So chora and topos are interrelated, but the interesting question is, does chora give rise to place or not? On one hand, we could just say, neighborhoods don't exist. They're purely, imaginary concepts like vampires. Yeah, vampires don't exist, but we all know what one is. Equally, we can say, neighborhoods do exist. And again, kind of substantively, people do feel that they have a neighborhood somewhere. They feel possessive of their territory, their neighborhood. But has that got any physical relationship with where they are? Or is that just kind of something to do with just how geographically close you are? Are you at the center of your neighborhood, and is your neighborhood like, kind of this big ring around where you are? Or does it actually move around? Could you be at the edge of a neighborhood, for example? So again, a lot of sociographers talk about topos and chora. And the interesting question is, does one give rise to the other one? And for many people, the answer is no. Like Emily Talon, her answer is no, there's no relationship between the two. But on the other hand, neighborhoods do seem to exist. We have these regions in London, and economist Webster in 2003 kind of goes, they are a major decision when you're buying a house. What neighborhood is is this house in? Is an important decision-making process. So that seems to give credence to the idea that neighborhoods do exist. They certainly have a geographic domain, but again, no one's very certain about where they actually are. So, for example, where is Chinatown? Is an interesting question. It's like, do you have a Chinatown in your city? Where is it? Where does it extend? So I think in many ways, a lot of these proofs from these social geographers actually are based on a false premise when we interpret them from the view of space syntax. So when geographers talk about space, they actually mean space as a coordinate system. So a longitude and a latitude, or an X and a Y position. For them, space is infinite. It's infinitely divisible. There are no limits, just like there are no limits to a size of a number, because basically you've got two numbers that can go off, or three numbers if you want to include height, that can go off in all dimensions. So they're using space as a very mathematical definition of space. Alternatively, in the world of space syntax, we tend to work with the more architectural definitions of space, where a space is a void defined by physical barriers. Now, again, this is one of these elephants, which is very big, and I don't want to go into deeply, but you can see from the world of space syntax that if we think of a place as a number of interrelated spaces, it is the relationships between those spaces that defines the space, and therefore a ship does have space. Equally, there's some evidence to show that when camps come together, particularly kind of Native American camps, the relationships between the various tents was fixed on a social hierarchy. So again, they would move around, but they weren't completely free to put their tent anywhere. You couldn't be that close to the chief if you weren't that kind of person. So again, there was a spatial relationship which were being maintained even though geographically they were in different places. So from a syntax point of view, we could say that there is some kind of relationship between space and place. So space being the more kind of physical element, and place being the more social side of it. So we're back to topos and core. Yes, so just what I said. Basically, this assumes that space equals a coordinate system space. And if you assume that is the correct definition of space, then that proof is pretty definitive. I would actually argue with it, which is actually we need to look at these things from a more spatial, syntactical point of view. Now, Bill did then come in, and a number of people in the space syntax community have begun to look at the concept of neighborhoods. John Perponis did some nice work in 1997, and he observed that many neighborhoods tend to be bounded by strong values of choice. Now, you could counter that. For example, in London, you've got Kensington High Street. Kensington High Street is a strong choice street in the middle of London, and yet Kensington is actually spread either side of this strong choice thing. On other occasions, for example, Oxford Street is a strong integrator, and there's definitely different neighborhoods above and below Oxford Street. John Perponis introduced this very interesting kind of idea, and it was interesting because he was trying to make these things syntactical. And again, if you're interested, refer to my PhD, because I look at a number of people in the space syntax community who have previously tried to look at neighborhood. Bill Hillier definitely introduced one of the most formative ideas, which is the one that got me going on this, was this idea of intelligibility. Now, for those of you that don't know, intelligibility was originally one of those ideas that kind of emerged as a way of explaining why dysfunctional housing estates were so hard to predict with space syntax. So let me just show you, I'm not too sure how many of you know about intelligibility, but forgive me for insulting your intelligence. These are two scattergrams of integration against connectivity. So each one of these points in that scattergram represents an axial line in this particular case. And each axial line has a certain degree of integration and a certain degree of connectivity. And Bill said that in well-formed places, there was a strong correlation between integration and connectivity. And again, this is all in Spaces the Machine. Equally said badly formed places, kind of dysfunctional housing estates, places we find hard to predict initially, have a very weak correlation between connectivity and integration. Does anyone want me to explain integration in more detail? Can we just kind of go with it as an idea for the moment?
I think that works, yeah.
I think that works. Good. Okay. So each of these points basically says, generally in a well-designed system, integration will correlate well with connectivity. So if you're on a well-connected street, it tends to be an important street. Whereas in a dysfunctional housing estate, you can be on a highly connected street. Hang on, let me just, you can be on a highly connected street, but actually its connectivity is high, but its relationship to the whole system is low. And that got me thinking about this kind of, what do we mean by intelligibility? And one of the ways we started to use it was this idea of, it was a measure of maziness. So it was a way of measuring how complicated or unpredictable an environment was, how difficult to navigate it was. So I became quite interested in this because on the one hand, if you have a small village and a large city, clearly the small village is going to be easier to navigate because there's less stuff to navigate. On the other hand, think about something like a labyrinth or a maze against an equal-sized, well-laid-out location, yeah? So with the same number of spaces or the same number of axial lines, we can create a maze, or we can create something that's quite readable and easy to navigate. So I ended up in my thesis talking about extrinsic intelligibility, which is basically intelligibility based on size, and intrinsic intelligibility, which is for a fixed size, how confusing or labyrinthine can we do this? So at that point, I was looking mathematically at how we could actually figure this out, you know. And again, if you want to check my thesis, there's an equation there you can use to differentiate between the intrinsic and extrinsic intelligibility of a system. However, in the process of doing this, I started to plot. So if we imagine we select an axial line in a large urban system, you can then look at, say, everything within radius 3 of that, and that gives you a subset of your axial map, everything within radius 3. And then what you can do is you can look at the connectivity and integration for everything that's within radius 3 of you. And that would generate a number from 0 to 1, technically from -1 to 1, but normally it's just 0 to 1. And you could apply that number back to the system. So, yeah, we'll come back to that. So when you do this, you generate maps like this. And when you do generate maps like this, now again, in terms of space syntax, we are now so used to looking at axial maps in so many skewed ways, we just read them immediately. And I apologize for anyone who's not used to looking at these axial maps. But for someone like myself or Bill or Alan or Julian, we looked at that and we goes, oh my God, it's captured Barnsbury. That blue area is Barnsbury. And the colors here are what is the intelligibility. So, you know, take one of those axial lines, find everything within radius 3, what is the intelligibility, and then apply that as a number back to the axial line. And it's like, oh, that's Barnsbury. Oh, that's Highbury Fields. Oh, that's Islington. That's Clerkenwell. So what seems to be happening is regions of constant intelligibility seems to be predicting neighbourhoods. And that was a complete surprise. No one was expecting that. And, you know, in many cases, in my particular case, that was a good example of information, you know, looking for one thing and finding something completely different. It was a complete surprise coming out of it. So what we can then do is start to go to neighbourhoods and then start to apply this to neighbourhoods. Now, this is a bit of a complicated example because actually this is Golders Green, and you've actually got multiple neighbourhoods there, partly because different parts were built at different periods. But again, you've got certain regions that were built as garden villages. This one's become quite integrated. This is Clerkenwell. And that led to the, well, sorry, I'm skipping ahead. Also, Yang and Hillier, Bill and Hal also started to do this. So my work was all with axial lines because no one had defined intelligibility for segments. Segments were new when I was doing that work. And so Bill worked with Tao, and they produced very similar things looking for neighborhoods. And they found a similar kind of relationship looking at neighborhoods. So again, look at the fuzzy boundary and spatial defining of urban neighborhood areas. It's a great paper. I'd recommend it. And it does segmentally what I did axially. But it leaves us with the question of, is this true? And, you know, space syntax is primarily an empirical subject where we need ground data to define whether or not what we're looking at is just something that's in our heads, imaginary pretty colors telling us stuff, or is it actually relating back to the real world? So for my thesis, the big question was, how do I get a real world neighborhood? There were multiple definitions. So this talk is not about the spatial correlates of neighborhood, but finding the evidence. That is another talk, which would take a long time to do. But, you know, feel free to invite me back at some point. So how do we find the neighborhood? Now, there's a lot of work on this. Kevin Lynch was looking at the idea of the sense of place. And what he did was he stopped people walking around in Beacon Hill, and he asked people to draw a map saying, where do you think this neighborhood extends? Where is Beacon Hill? Can you draw on this map where Beacon Hill is? So basically he ended up with something like that. So people would draw a boundary which represented what they thought was Beacon Hill. Now, again, there's not a lot of detail in Lynch's work about this because he was looking at many different things alongside neighborhood. And he was analyzed those maps. But you could say methodologically, if you just stop someone in the street, are they actually a local? Is this actually their neighborhood? Have they just stopped a random stranger, and have they done that? So we don't know, because that data is so old, how reliable that is as a thing. But it certainly, as a technique, is a great technique. Lee also went on to do a similar sort of process. So again, follow that line up. So what Lee did was he went and knocked on people's doors and said to whoever was ever in, can you draw on this map where you think your neighborhood is? Okay. And again, we don't have enough strong data about how methodologically that work isn't very clear in places. One of the things that Lee does say is, oh, wow, you come up with a huge mess. You come up with a huge mess of polygons, yeah? And it's like, oh, what do I do with this huge mess of polygons and where these neighborhoods? I've got no idea, you know, what do they mean? What do they think? He was asking them with a number of different questions. So generally when people, particularly sociologists, have done this, they kind of go, you end up with this mishmash of circles. You know, what can I do with that mishmash? Taylor did some great work in 1984. Again, he was sort of talking to people, asking them to do this. Guest and Lee, again, worked in 84. And then in 2000, Dan Montello comes along, and he creates this interesting method where he's looking for where is downtown. And somebody who says to people, he stops them in the street, and he kind of goes, tell me where you think the neighborhood extends out to, yeah? But also tell me where you're definitely 100% sure the neighborhood is, and then finally give me the center of your neighborhood. And he finds things like people's centers generally align. So that was quite interesting. So it seems to me that people aren't drawing random polygons now. They're representing some mental representation in their head, which for the first time in their lives, they're then trying to put down on paper, and they're not doing a very good job of it. But things like local centers, they align well with. So there's definitely some shared idea here. So again, what we're looking for here is a neighborhood should be something that you're inside of. It should have kind of extents. You should know when you're in and not in your neighborhood. It might not extend. maybe extends to places you haven't visited. So if you haven't visited that back alley, that can still be in your neighborhood. It's still part of your area, but you might not have been there. But also, it's not just you're in the center of your neighborhood and it's this huge kind of just region around centered on you. Okay, so you can be offset from your thing. And we'll come to a few more papers about that towards the end. So Dan did some great work. Okay, so what did I do? So what I did was I created what people now nicely refer to as the Dalton postal method. Why did I do this? I did this because I wanted to talk to people. I wanted to get locals to fill this in. So I could have gone repeatedly around again and again and again and again in order to get people to fill in the form. Because, not everyone's in all the time. So that would be quite a lot of work. So what I did instead was I created this postal map. And then I created this. Hopefully you can see all that. Okay, so you can see on the side, in fact, I'll hold one up. Here you go. Here's an example. On the side, it says, my name is Nick Dalton. I'm a researcher at University College London. I'm doing research into neighbourhoods. I'm trying to find out where people feel their neighbourhood is. There's no right or wrong answer. On this map, would you please draw a line around the area you think of as your neighbourhood? By neighbourhood, I simply mean the part of the city where you live. And then I asked 3 or 4 demographic questions. The first one was, do you think you're a local? How long have you lived there? Does your neighbourhood have a name? If so, what is it? Now, again, from a sociological or psychological place, naming things makes things. So if something has a name, then it tends to kind of exist. We don't normally name things that don't exist. So anyway, you go around, and there's a couple of more hints. There's a couple of more things which I'll tell you. You go around, you put the blank card through people's doors. And thankfully, UCL had a free post system. So basically, all I had to do was print all the cards out, put free posts. If you're going to do this at UCL, if they still have the free post system, go and talk to the post office, the post room, and they will basically give you the yes or the no. And basically then all of these cards will be collected for you. So you end up with, a couple of weeks later, you end up with a bunch of cards. Fantastic. So here's my data with all the boxes written on it, blah, blah, blah. There we go, all this kind of stuff. So yes, so then you're left with a couple of problems. The first problem is, as Alan said, no one can read a map and people don't know where they are. So that was an interesting question. He was very firm that people were basically were unable to respond correctly. Yeah. So the solution. So the solution to this was actually on each of these cards before I posted them, I had an ultraviolet marker, and I would mark the street of the place I was posting it from. Yeah, and then when I received it, I would then apply an ultraviolet light to it to see, because I asked them to actually tick the street they lived on. And if the street aligned with my marker, then they knew where they lived. And that for me was a kind of test to see if they could actually read the map. Now, in practice, no one got this wrong. So basically, the point is that the people that respond are the people that can read maps. The people who can't read maps don't do it and don't send it off. So you actually get quite a good thing. Now, in terms of post, you do get a very good response rate. So that was actually quite useful. Normally, you get, if you're doing marketing, you know, if you're doing free posts with marketing, the people in the post room said you'll get like 1 or 2%, but I actually got 10 or 15% of these cards coming back, depending on the region. Some of which are just really good. I mean, obviously you've got problems, which is like, this is scientific data, but like, oh, this is lovely. this is really fantastic stuff. It's like, this is my region. It's like, okay, this is where I am. This is great. So I always wanted to turn these into an exhibition of sorts, but that's not ethically allowable, which is a shame. So yeah. So once you've done all that, you go back and you trace all of these polygons back onto the original map, and you end up with something like this. Now, remember, the initial point about this was trying to correlate that with the numbers being produced by the machine. So what we want now is something that gives us a single polygon, which is a kind of average of everyone's ideas, and then allows us to compare that to the reality. A quick tangent, if we may, you will notice that, for example, this is Golders Green Road, and that is actually quite a strong integrator. So that follows John Paponis's idea of strong choice values becoming edges of neighborhoods. On the other hand, this one is also a strong integrator and a strong choice value, but you notice quite often people have gone around it. So again, so the question then becomes sort of, how do we get these things back to a single polygon we can use as our kind of average neighborhood? There's more ways you can do stuff with this in a moment. We'll come back to it. So let's get on. So we want to find some way of doing this. So that's the Dalton postal method. If you want me to put the slides up anywhere, I can do a bit later on, Kimon, yeah? If people want that. But you can search for that on the UCL library. It's part of the doctoral thesis. It's all there. Right. Before I move on, there's also more modern digital methods. So von Strupenagel did a lovely online version of this. So he sends out an email or communicates to people in a region, and there's a piece of software where you can geographically put in where your neighborhood is. And again, he wrote a fantastic paper called "Your Neighborhood is Not a Circle and You're Not Its Center." And the fact that you're not at the center, as that example in his paper goes, does show you that the neighborhoods are shared between people. You know, that if my neighborhood was just kind of something related to just me, then I would be at the center of my neighborhood. If I'm on the edge of the neighborhood, it tends to say that the neighborhood exists and I have a relationship with it. So again, that's another good paper, and I definitely recommend it. But again, with the von Strupenagel process, the online digital method collects info in a different way, but you end up with the same problem of how do you actually figure out what is the average of all these polygons? So how do we resolve the single boundary as a way of analyzing the components? There we go. So my first method is called the radial dissection method. So what you do is you begin by picking a point that's in all of the polygons. And then you draw, so we pick a point in the middle of all these polygons, and then we draw a line. Pick a common center, draw a radial. Oh, there you go, there's the radial. It doesn't matter which direction it goes in. We, often you just start off horizontally or vertically, whatever. And then what you do is you measure the distance from this common center to wherever the polygon, so you can see there the orange polygon intersects the dashed radial line, and it produces a distance. Let's say that's 34 millimeters. The green one would be 38 millimeters, and then the purple one would be, let's say, 45 millimeters. The actual numbers don't really matter in this particular case, but they're just some measurement. What we can then do is we've got three numbers. We can find the average of three numbers. So we can say, oh, what's that? The average is going to be 35.6, and we can create a dot at 35.6 along that radius. So that's the average at that particular of that particular line, that particular radial. So then what do you do? Well, keeping the same center, you just increase the angle of the radial. Oops. Increase the angle, and repeat the process. So you end up with a new polygon, which is basically the average by averaging out the distances of all the other polygons. There we go. Repeat until you got 360, you know, do it in 5 degrees increments or 1 degree increments, whatever you want to do. It's kind of entirely free. And you end up with a polygon. So that is what I'm going to refer to as the Dalton average radius. Now, Montello and Bayer, Crystal Bay, came up with some critiques of this. They sort of said, how do you select the common center? And it's actually, it's a good point. You could take the gravitational center of all these things. It does assume that there is a common center, which isn't always necessarily true. If we look at, say, this example, going back a few slides. Keep going. Let's go back slides. I'm sure. There you go. You'll see in this one that there are these 2 small red and orange, very local things. So there's no common center for all these ones. Again, where did these small ones come out? They come from people treating their neighborhood as where their neighbors live, which is like, that's a reasonable definition of neighborhood. So their critique was, where do you get the center from? Where do you get the center from? And what was the other critique of it? I've forgotten now. It assumes there is a common center where it's sent. The other major problem is, what average do you use? Because you could have the mean, the mode, the median. So again, if you do that, you'll end up with different polygons, some of which are kind of look more realistic than other ones. Okay, so Montello and Bayer came up with what they called the raster method. So what we do here is we have a series of points. And what we do is, for each point, we count how many polygons it is inside of. So the ones on the outside have 0 polygons. The one inside the green one, so that's in the gray one, isn't the light gray one is inside the green one. So that's got 1 polygon it's inside of. The next one, the medium gray one, has got 2 polygons it's inside of, and then you have 3 polygons, and that's the limit. And then you keep making points in space, doing point, and then it dies off again. This is a good method. It's kind of an equivalent of doing this. So, and then what you say is, like, what grade of black am I going to declare as being, you know, essentially in the polygon, and what grade of black is kind of not part of the system. So you pick a kind of percentage, like 80%. I want 80% of the polygons should be here. Now that's quite nice. It's quite a nice mechanism. So I did a radial version of that. So you do the radius, but this time you sort them and you pick the 90% closest to the beginning, the center of the line. Okay. So what's nice about that is that the edge of the polygon will always be on side of somebody's line that they've drawn. So that's quite nice. So we end up with a large number of different ways of doing this, and we end up with the question, which one is right? So the answer to this is, you create an online questionnaire, you send it out to the members of the space syntax community, you send it out to members of the general public, you explain what you're doing. You do this for a number of different locations. So I've only shown you one, there were 3 locations in the experiment. And then you say, which one of these polygons most represents the other ones? And again, if you follow the paper at the end, you can see the questionnaire and so on, if you want to follow that process. You can see here, can you actually see my cursor at all, Kimon? Can you see my cursor?
Yes,
you can, good, right,
yes.
okay. So let's start off with the worst one. This is the KME ones. k-means clustering ones. No, k-means, yeah. So this was a very advanced AI technique for finding the kind of optimal average. And if you notice what it does is it's very unstable. It produces these very spiky polygons for various mathematical reasons I don't want to get into. It's like, so it kind of, this one is a line of agreement that people like, but then here it kind of can't decide between this line and that line. So it's making all these, making a very spiky thing. So most people rated this pretty badly. Another really exotic mathematical way that was derived from another paper was using a Gaussian clustering. Now, again, I don't want to explain the maths of Gaussian clustering. This one does a little better. It follows the main street here. Everyone agrees that's the main street. It kind of goes out here. It kind of tucks in there. That's not too bad. And then it has this kind of interesting dramatic line here where it kind of pops back in the center. So it's kind of thinking, yeah, that's good. But then suddenly going, actually, no, that's good. You end up with this kind of line that kind of doesn't really seem to represent what people think. So that's not bad. We have my original averaging system. So that's the one I used inside my PhD thesis to test against the data. And this is the Montello averaging system. So this is basically a version of the Montello raster grid. So you present this to a large number of people, and you say, which one do you think the best one is? So I'm going to give you a second to decide which one you think is more representative. We've got this kind of gray line here, the blue line here, the green line here, and the magenta line here. So just for a second, say to yourself, which do you think most represents the average of all these kind of polygons? Okay, so what were the results? Generally, people favored the Montello grid version, the radialized Montello version. That seemed to be slightly better than the Dalton version. People didn't like people thought the Gaussian was okay, and no one liked the k-means clustering. I think that's kind of fairly obvious looking back on it in retrospect. So as a method, you could use the Montello one, or you could use the average radial one. They're not that different. But I personally, if I was going to do this again, I'd be using the Montello grid purpose. It produces nice polygons, and it never produces fake polygon edges. So with that, you can then go back and you can say, okay, this is my average polygon, this is my average neighborhood. What does this tell me about where the neighborhood is? What does this relate to spatially? Okay, so that's what I did in my thesis. And we've got about we've got till the hour, haven't we? Yeah, I've got 15 more minutes.
Yes.
Okay, so again, this is the paper using both space syntax. The one I published was on the lay deciders. It produced the same results, so it's kind of fine. If you want to make a reference to it, whatever, this is the paper to look at. If people would like software to do this, let me know and I will make the software public. But let's move forwards. It's that one. Oh, I did a nice animation for that. Yeah, so this is the best one. There we go. Now, I want to touch on something that I didn't do as part of my thesis, but as you're going through all the slides, as you're going through all the postcards and start looking at them, it gets quite interesting. The one I didn't show you is Clerkenwell. Now, Clerkenwell is a good example of what happened to most people when they did this. They kind of produce these kind of diagrams, and each of those colors is a unique feedback from Clerkenwell. I've put it on top of the axial map of Clerkenwell so we can have a good kind of representation of what we're doing without infringing the Ordnance Survey. But you end up with this kind of, oh, wow, what is this telling me? This just seems to be a mess of polygons. How can there be a neighborhood here somewhere? And actually unpicking these is really interesting. So let's deconstruct these particular polygons. If you look at them, so as we're working, you've got to realize people work with different definitions of neighborhood in their head. The first one is the neighborhood is where my neighbors live. Literally, it's the next door people. So that's one representation. There is the received version. Again, there's a lot of technical literature about this. So basically, there are lots of things telling you where your neighborhood is. For example, postcodes, or there might be a local school. So you might want to have the Clerkenwell School. So that's an official received way that's telling you what neighborhood you are in, okay? And you just take in whatever the government tells you, or whatever you're told is the neighborhood. Now, remember, you know, if you're living in somewhere like London, Islington is a lot bigger than it was 50 years ago, because Islington is desirable, and therefore people tell you, estate agents tell you, oh yeah, this is in Islington. Everyone else might think you're in Stoke Newington, but they're telling you this is Islington because this is worth more in Islington. So again, you have this received notion of where your neighborhood is. The other region is, where do I feel at home? What is my territory? You might not have visited every seat, but it feels where you are. So there was a famous case of one person kind of going, how dare you come into this neighborhood and tell us what to do? And it's kind of like, well, how are we supposed to know where your neighborhood is? You know, it's like, it's just part of the urban fabric. It's continuous. Where are the edges? So it felt rather unreasonable. That person genuinely felt they knew where their neighborhood was, and these people coming into it had definitely intruded on their neighborhood, okay? There are ways you can do this, but unfortunately they're difficult to operationalize in terms of writing an experiment that would actually pass ethical procedures. So, for example, one way people identify neighborhood is if there is a threat to your neighborhood. So, for example, if you said, okay, they're going to put a needle exchange here, are you going to campaign against it because it's in your neighborhood? Yeah. So you find something that not everyone doesn't want, and then you ask them, is it in your neighborhood? Now, of course, you can't do that because people would be thinking, oh my God, the government's going to push a needle exchange, or a youth offense center, or whatever other desirable thing you can invent in that particular location. Yeah. You could say, you could identify, so for example, one of the ways people identify neighborhoods is something was going to be knocked down. Yeah. It's like some iconic neighborhood shop, some iconic neighborhood tree is going to be destroyed. Would you join the campaign to stop this from happening? Obviously, if it's not in your neighborhood, you're not going to bother. But if it's in your neighborhood, that is a test to see whether or not your neighborhood is part of that kind of process. And again, equally, you could pick, one way you could do this is by saying, oh, these 4 locations that I'm going to randomly pick have been selected by your friends, and they've said, oh, I've just moved into your neighborhood, but I'm living here, and it's up to you to decide whether or not that particular location is in the neighborhood or not, and they've been ripped off. So again, that's a more operationalizable question about what is in and outside your neighborhood. But again, that becomes tricky in terms of defining how many, because people could answer specific questions like, is this in your neighborhood? Yeah. Is that in your neighborhood? No. But actually making that into a polygon boundary would become tricky. But again, it's something someone might want to experiment with and come up with ideas for, in terms of getting a much better, richer, more fixed definition of neighborhood. Okay, so that's one kind of area, which is how do we get people to say what their neighborhood is? Going back to Clerkenwell. So as we start to unpick Clerkenwell, you'll see these different definitions in operation. So for example, here Clerkenwell is in the center. Sorry, this is Clerkenwell as a region, and they've picked quite big groupings here, but they overlap. And in the center is quite a large, generous area. We'll come back to that in a few minutes. Equally, we get these people. Is that one? Yeah, yeah. We get these people who basically have this kind of northern version of where their neighborhood is. And matching that, we have these people who would do the more southern end of it. Let's go back to this. Now, what makes this interesting is all these people feel they live in Clerkenwell. So when you ask the question, where is your neighborhood, they would say Clerkenwell. But the interesting thing is they all share this common street, which is Exmouth Market. So Exmouth Market, if you don't know London, is a famous, now pedestrianised street, which was very famous for having a marketplace for hundreds, if not longer, years. So famous Market Street, it's now become a bit of a kind of bijou, maybe, you know, it's a nice place to go on a Saturday afternoon, but it definitely becomes part of people's neighbourhoods. Both north and south all feel that this is part of their neighbourhood. But then you would expect that it's part of, you know, it's a major local facility and they're both sharing it. So yeah, Exmouth Market becomes the edge of their neighbourhood, but it's definitely part of their neighbourhood. Okay, notice these people, they've actually gone over a couple of more strong integrators, partly because they're possibly including the Angel Tube Station as part of their neighbourhood, which kind of seems reasonable. This person is a bit smaller. This person's a bit smaller. And these people are a bit more generous. Again, they've got Exmouth Market slap bang in the centre of their neighbourhood. And again, these people are the same, except they live south of Exmouth Market, so they're kind of pushing it to the north and making a system. Okay, now the interesting ones were, for everyone else previously, they said, oh, I live in Clerkenwell. These people started reporting interesting one. Oh, here you go. Here's one randomly picked from my stack. And they say they live in Amwell Village. Now, Amwell Village is an interesting concept. And it was I was quite surprised by this initially because this is actually quite a small, tight area. And having so many people identify this small subgrouping as their neighborhood was interesting. In terms of the software, my software that does the calculations had a radius factor. And if you reduce the radius, you did get a neighborhood in this area. So that was interesting. But they have a very local neighborhood. What was also interesting was going back to naming as being an interesting factor. They talked about it as being the square, the village, Amwell Village. There was a whole bunch of different names for the same area. So these people weren't talking to each other because they didn't have the same name. What was interesting about this area was it had recently, when I did the test, did the survey, had actually gone from the 1980s social housing to being sold off and then being privately owned. So I'm hoping to finish on time. Now, interestingly, before the 1930s, there was an area called Little Italy. And one of the bits of Little Italy was that area. So what we would now call Amwell was actually historically from the 1800s called Little Italy. Again, there's another Little Italy nearby, so I'm not sure if the records go back that far. But what seemed to happen was there was this local neighborhood. It got cleared out in the war. It got converted into social housing. The social housing then got gentrified and turned into housing again. And then this neighborhood was springing up as I was measuring it. And people were actually saying, oh, please contact me about this. If you actually look online now, there's an Amwell society. So there's a group of people in that area who formed a society out of this. So what's interesting about that is the idea that actually neighborhood existed. It had an affordance, but it was only when people could be wealthy enough to start making websites about it and kind of giving themselves names that this could actually emerge. There you go. There's a small short thing about that. So that was a merging place. So I was seeing the birth of a neighborhood, which was very interesting. Actually unpicking all these numbers, is actually a very interesting and informative behavior, which I think would actually make some very interesting piece of research. Okay, so I hope this has all excited you. If you're looking for more information about the method, then go to the PhD thesis. It's all in there, along with far, far more. And then if you're interested in form the analysis, which is like how you go about doing it with the stuff, I've got a more recent Environment and Planning B publication on that, which kind of makes reference to some of the techniques and stuff. But again, the majority of the technique is actually in the Dalton thing. But I've actually told you most of it, how to do it.